So
Alright, so we'll get going. So today's lecture is plutons and intrusive activity. So this follows on from last week's lecture on the volcanic rocks. So the first part of the lecture we'll do a little bit of a review over the classification and the naming of the igneous rocks. And then we'll look more in specific focus at the intrusive activity and how these intrusions actually are emplaced in the Earth, and the differences between how we classify them in terms of shape, size, and orientation to the bedrock, the surrounding country rock. And then we'll look at how a magma evolves and how we can explain some of this difference in composition. So last week we focused on the volcanic rocks and the extrusive rocks, so those that formed from magma that reached the surface. And this week we're going to look at the rocks that actually form and crystallize underneath the Earth's surface, so they never actually break the surface. So they're the intrusive or plutonic rocks. So when we looked at naming igneous rocks last week, you can focus on two things: the mineralogy of the rock, so the minerals that are in there, and also the texture of the rock. So this is a review of the mineralogy of the rock. So we had those dark minerals which you started to see in the practical classes. So they were olivine and pyroxenes. So they're the ferromagnesian minerals, or the dark minerals that you see in the rock. Then we've also got the light-coloured, or the felsic minerals. And someone in my class last week told me a good way of remembering that. And that's if you're pale, so if you're light-coloured, you feel sick. You might feel sick, felsic. So if you can think about that. She's sat over there, so I can see her, so thanks for that. So then if we've got with the proportion of these felsic to mafic, so the dark ones to the light ones, can then help you classify the rock in terms of knowing what its composition would be and therefore giving it a name. So where we have mafic rocks, so dominantly composed of these dark minerals, in a coarse-grained rock that would be a gabbro, whereas we learnt last week there would be a basalt in the fine-grained rock. Then on the other extreme, if we've got lots of non-ferromagnesian minerals, so a lot of these light-coloured felsic minerals, then if we have a lot of quartz and feldspar, we might term that a granite if it's a coarse-grained rock, or it'll be a rhyolite if it's a fine-grained rock. So when it says mineral mode, which is what we'll use on classifying these coarse-grained rocks later in the lecture, then it just means, by mineral mode, just means the amount of that mineral in the rock. Okay? So the general characteristics of intrusive rocks: they cool more slowly because they don't quite reach the surface. We'll see when we do the classification of these that they often have a wider range of composition than what we've covered in extrusive rocks, in the volcanic rocks. And we often get that the volatiles that would have escaped possibly in the volcanic rocks and led to the kind of eruptive behaviours, we see that they don't escape from the intrusive rocks. So a lot of these volatiles are contained within the intrusive rocks, or the plutonic rocks. So we get hydrous minerals commonly more formed in these rocks than in the extrusive. So hydrous minerals such as mica and amphibole. So you often see these in granitic rocks. So this is just summarising from last week again, so just showing you the difference between if you have the same sort of composition, so if we have the mafic, intermediate and felsic composition or mineral mode rock type, then whether it's coarse-grained or fine-grained then gives you this classification. So you can see clearly the ones on the top row, these intrusive rocks, have a coarser grain size. You can actually see the minerals within each part of the rock. Whereas the extrusive equivalents, the fine-grained equivalents, you can see that they're very much finer grained and you can't see the individual minerals with a naked eye. And there is a little bit, we have kind of intermediate grain size, which we'll look at a little later on in the lecture today. So the things that can affect grain size, we mentioned a few of these last week. So this was the volatiles, the silica content, and the viscosity. There's also a few other ones and a few extra ones, so such as the concentration of components in a melt. So obviously if something's more concentrated in an element or an ion that goes into a mineral, you have more likelihood that you'll get that mineral crystallizing. And also whether you've got space for crystallization. If there's a lot of space, you might form bigger minerals. If there's a smaller amount of space, you might form smaller minerals. And then the other one is the nucleation ability. So how easy it is for that mineral to nucleate, to actually start to crystallize. So that depends on the thermodynamic properties of the, yeah?
When you say larger and smaller minerals, do you mean on the molecular level?
On the actual physically you can see level. So just on the grain size of that mineral or within the melt. Yep, so there's a variety of things that are going to affect that grain size. So pegmatite, this is one that you'll have seen on the campus excursion when you went round in that first, I think it was the first week or second week. And you'll see that in some situations where we have favourable conditions for large grain sizes, so you can see the scale here is about 6 centimetres along the bottom. So these are very big crystals. So pegmatites are what we call it when you get these large crystals forming from the melt. And these usually form in the late stages of crystallization. So it's when you've got concentration of volatiles at the end, once all the minerals have crystallized. And they're very common in granitic magmas, and you can see here the kind of grey, dark-looking ones are the quartz, so that's the SiO2, and then the pinky-looking ones are the potassium feldspars that you've been looking at in the practical. So how do we form these? And we're going to spend a bit over this lecture just looking at how we emplace these magmas, so how we actually get them there in the first place, and then how we get them to the surface to see them. So if you think about the volcanic activity we see on the surface of the Earth, that's related to much more magma movement and magma storage underneath the Earth, and most of that magma is placed at depth, and it cools before it reaches the surface, as we already mentioned. So once this igneous body is cooled under the surface, we then call it a pluton. And the way to remember this is that it's named after the Greek god of the underworld, Pluto. So how do we actually get it into place and move it in the Earth, these big bodies of magma or plutons? Well, when the magma is at depth in the Earth, it's much less dense than the surrounding rock. And because at depth, so we're not talking at shallow levels, we'll do that next, but at depth in the Earth, the increased temperature and pressure causes the rock, the solid rock, to deform plastically. That just means it can kind of bend and move quite easily. So therefore, this buoyant magma, which is in red in the diagram, can kind of just push its way through as it's more buoyant and it tries to rise. It can kind of shoulder its way through, and the plastic deformation occurs in the country or host rock, and that's what we call the rock surrounding these plutons. We call it country or host rock. So you can see the diagram there, the buoyant magma has managed to push its way through and is moving slowly towards the surface. But when we get to more shallow depths, the host rock or the country rock is a lot more brittle. So if you think of it, if you had a chocolate bar and you put it in the microwave, so where it's hotter, and then you can kind of bend it and mold it. Whereas if you took that chocolate bar and then tried to push it, if it wasn't heated, it would just snap. So you can think of it, depending on what the host rock or the country rock is like, depends on how easily or what happens to that rock itself. So at shallower depths, where the host rock's cooler, it exhibits a brittle, so like a snapping or fracturing deformation when the magma tries to move through it. So the magma, which is the red blob within the diagram, it causes the rock to thermally expand from the heat. So the host rock thermally expands and starts to fracture. And then that magma forces its way along those fractures. So it injects along there, so the fluids and the melt will inject along there and then start to break up that host rock or that country rock. And this process is called stoping. And then what happens is some of those blocks can actually dislodge and fall into the magma, and if they're more dense, they'll settle to the bottom of the magma. And sometimes there's a limited interaction between that because there's just not enough heat within there to react and melt the country rock. You might affect the margins, but you'll not necessarily melt and mix in those blocks that fall into the bottom. And by this process, the magma can then rise to the surface. So it kind of just forces its way through these fractures. So that's how it can move and how we emplace these magmas. So if we look at how we classify them, we can classify them based on their size, on their shape, and on their relationship to this country rock. So we'll focus on the shape and the relationship first, and then we'll see a few examples of different sizes. So in terms of the shape, you can have a tabular shape, which is like a sheet-like, or if you think of it, a tabletop, kind of this rectangular shape. Or you can have massive, which means it lacks internal kind of structures, and you can think of this as a big blob of magma. So these are these two main, yeah? Yeah, it's not, so in terms of massive, it's not referring to its size, but you'll see this a lot when you look at rocks. If they don't have any physical internal structure and it all looks pretty homogeneous, this will be described as a massive texture. It's just the terminology that we use. So you can classify them on the shape based on this tabular or massive structure. And then with orientation to the country rock, so this now is so this is looking at probably the shallow areas in the Earth. You can see that so on the right-hand side where we've got D and C, these are our magmas, and the country rock are the blue and kind of purpley pink layers. So you can see that if you cut across those layers in the country rock, this is called discordant structure. So you cut across those sedimentary layers or pre-existing layers. However, if you form parallel to those, we call them concordant. So you can have concordant and discordant plutons depending on their relationship to the country rock. So in terms of the tabular types that we have, we've got a discordant tabular feature, which we call a dike, and we'll show an example of this on the next slide. If it's concordant, we call it a sill. So these are these tabular ones. And then we have something where it's a bit similar to a sill, but what happens is as the magma is being injected along parallel to the bedding, say, of a sedimentary rock, so much magma is injected that it forcibly, instead of moving laterally, it starts to kind of balloon up the sedimentary layer above. So you get this arching and this doming of where the magma is being injected in. And they can form quite large structures. These laccoliths is what we term them. They can look like mountains in themselves, so they can be quite big structures. So here's just a couple examples of dikes. So we've got obviously two spellings here. The first one kind of the British-Australian spelling, and the one in brackets is the more American spelling of this. So you can see that these are, you can see on the left-hand side, you've got some kind of reddy coloured, almost parallel bedded sedimentary unit with this darker coloured dike cutting across that. So you can see it's not quite vertical, it's more of a 45-degree angle, but it's cutting across that bedding in the country rock, so this one's a dike. And then you can also see on the right that sometimes these dikes can be more resistant to erosion than the surrounding rock, so they can form prominent features in the landscape. And sometimes you can go to these areas where these are exposed and they just look like man-made walls going across the topography. Whereas sills, so we know that these ones are the ones that form parallel to the bedding or to the orientation of the host rock. So you can see we've got two examples here, one from Salisbury Crags in Edinburgh, and I used to live just across the road from this, so I had this view out my bedroom window every day, which was pretty nice. And then the other one is one in Salt River Canyon in Arizona, and this is really long. This is tens of kilometers long, this sill. And you can see that sills often might look like lava flows as well, because they're kind of parallel to the respect to the bedding that was there before them. Sometimes it can be hard to tell the difference between what a sill and what was a lava flow, so we'll spend a slide just looking at that in a moment. So one other thing that's very typical in sills is this columnar jointing that we touched on last week in the lava flows. So if you remember, we did the kind of typical structure of a lava flow, and you had these columnar joints in there, these cooling or shrinkage cracks that we said were similar to if you were stood on a dried up lake bed looking down, and you'd see these polygons of shrinkage cracks, where it's the same for the lava flows, it's cooling. So you can see that this is another thing that's common in sills. So it might be another thing that makes us think, do we have a lava flow or do we have do we have a sill? So one way you can tell, one thing that can help with how to tell the difference, is that because sills form a little bit lower, they don't quite breach the surface, there'll be shallow levels in the crust, but it might be sufficient in that the grain size is just that little bit coarser than you would get in a lava flow. So you can see here we've got fine-grained on the left, which is our volcanic rock, and coarse-grained on the right, our plutonic rock. So for the same composition, we've got basalt and gabbro, whereas we've defined a medium-grained rock here called a dolerite, or in the US it's called a diabase. And this is our medium grain, so a medium grain size of the same composition. And this is common, the common rock type that you find in sills. And the Egyptians, that's a photograph of a dolerite ball, which the Egyptians used to cut kind of the granite and some of the rocks. Yeah?
One on the left and one on the right broke up a term, volcanic and plutonic. Why doesn't the one in the middle have a?
Well, it's a plutonic rock, but it's a sill, so I was just trying to show you here the difference between the two end members. Oh, and the other thing I should just say, the other thing that can help you tell the difference between a sill and a lava flow as well, is that in a sill, you remember when we looked at the pillow lavas last week, you had these chilled margins, which were very fine-grained margins where it cooled very quickly, so you got this fine-grained size. Well, often on a sill, if you think about it, it's been injected and it gets put against these cold host rocks or country rock sediments, you can actually get on the edges of both the top and the bottom this finer grained chilled margin, and then it would go a little bit coarser grained in the middle. So whereas a lava flow, you wouldn't expect to see that. You'd probably expect a more rubbly top and more broken up top and base to the lava flow. So that's something that if you see a cross section through, can help you distinguish between the two. So that was the tabular plutons. Now if we move on to look at the massive plutons, so these without any internal kind of structure to them, then we have batholiths and stocks. And the only difference between these two really is the surface exposure. So a stock is so these are all plutonic bodies. So it's a plutonic body with a surface exposure of less than 100 kilometers squared. So that's a stock. Whereas the batholith will be one that has a surface exposure of greater than 100 kilometers squared. And whether or not you see, so you might define something as a stock based on what its present exposure is at the surface, but actually it could be a batholith just below the surface, and with a bit more erosion, it might then be classified as a larger structure. So it all depends on the level of erosion as well and what's exposed. But the picture on the right just shows the batholiths in red along the western coast of the US. So you can see these form a lot of the mountain ranges in that area. And they frequently form the cores of the mountains. And these batholiths are typically more evolving composition, so it means that they're more felsic in composition. And we're going to do a little bit more about that in a few further slides. And these can be emplaced over millions of years it can take to form where all these batholiths are today. So when you put a big body of magma high in the crust, what do you do to the surrounding rock? Well, we've shown that you might fracture it, and it might fall to the bottom of the magma chamber or the magma area as the magma moves towards the surface. But you can also bake the rocks. So if you think you're providing a lot of heat to this shallow area that's quite cold relatively and brittle, then you where's that flashing? And then you bake the surrounding rock. So we call this, don't know what's happening there. So you bake the surrounding area, and the area, so this is a form of metamorphism in that you're heating, and this is called contact. So you think of it as the magma in contact with the rocks. So it's called contact metamorphism. And it just shows you an example there of what the rocks then would become. So if they start off as limestone, you turn them to marble. If they start off as sandstone, it turns to quartzite. And I think either Nathan or Juan Carlos will do a bit more about metamorphic rocks with you in the coming lectures. So this just summarised the relationships between these tabular and massive plutons and how they are in place and their relationship to the volcanoes on the surface. So you can see what we'll start off with if we look at the surfaces. We've got composite cones, these are volcanic cones. We might have cinder cones, and then these could be fed by at depth by either dikes or might be fed by larger magma chambers below the surface. And then over time, as this system stops supplying magma and it stops being active, you'll get crystallization and then erosion. So you can see that the surface now is weathering down, so it's eroding down and exposing some of these features like the laccolith that was in the last slide, and the volcanic necks or volcanic plugs are now exposed. And then some of these feeding dikes are also exposed. And then with further erosion and then uplift, tectonic uplift, we end up with then seeing this internal part of the plumbing system, which is the batholith. So then we'll see that exposed. So in terms of the large intrusions, so these batholiths or larger plutonic intrusions, we're going to look at two main types. So one being layered mafic intrusions, and the second one being granitic batholiths. So we'll look at each of these in turn. So in terms of layered mafic intrusions, these are quite common. They can be in different areas, and what it is you have this seemingly primitive magma type, so a basaltic injection of magma, and then it just seems to crystallize in place. So they often form these funnel shapes, as you can see here. So this is a schematic section through the muskox intrusion in Canada. And you see this funnel shape to it. It's actually being faulted down on the left-hand side. And what you have is this marginal zone around it, which isn't layered. And then you also get a layered series within there. And what we can see is that the composition of this layered series varies from the base to the top of the intrusion. So we call it a mafic intrusion because the initial composition was mafic of the magma. But then what happens is we've ended up with these rock types that range from ultra-mafic, so very mafic, through to mafic, through to actually felsic. And we'll explain in the next slides how we can actually do this. And the layering itself, and why you get the layering itself. So if you think about, you can see here, I'll go back to this slide. So if you look on here, we've got dunite towards the bottom. It's formed most of the majority, the middle to lower part of the intrusion. Now dunite itself is a rock type that's composed of over 90% olivine. So the question is, how can we get such a rock type when its melting temperature for that composition would be way too high than what we can actually physically get? So the explanation for this is that you form olivine pretty early on in the crystallization, and that is denser than the surrounding melt, so it settles to the bottom. So you get these concentrated layers of olivine. So it doesn't mean that the magma itself was of that composition, but what you're actually seeing is a layering or a settling out of those denser, earlier formed olivine crystals, which then, once crystallized and held in place, look like they're a very olivine-rich rock type. So you can see on the right, so left-hand side is just a picture of this dunite. So this is a very olivine, so you can see it's that green-coloured mineral, and it's very olivine-rich. And then on the right, this is from the bushveld, and it just shows you that you can get different layers, or it shows you the detail of the layering. Yeah. Oh, just stretching over there.
Yeah, I was going to ask, according to Bowen's reaction,
Yeah.
is that really possible?
Yeah, Bowen's reaction is going to be 2 or 3 slides down the way, a few slides down the way, so we'll go through that. And if you have any questions after that, you can put your hand up. Okay, so you can see on the right-hand side what we've got are chromite-rich layers. It's an oxide mineral that's formed, so that's pretty dense and sank. And then we've got plagioclase layers, rich layers trapped in between that. So this is from the settling out of different minerals as they've formed over a range of temperature when cooling. So this is where we start to get on to how you can explain having ultra-mafic, mafic, and felsic all within the same body from the same magma. So if you think that you start to slowly cool, the early form minerals might be removed from the melt. So we know that olivine is one of the earliest minerals because it has the highest melting point. So if you remove olivine from a melt, so this is our big magma body on the right-hand side, this red, full of all these ions that you find in the minerals. And also you can see that those little pyramids are a silicon-oxygen tetrahedron. So these are our building blocks. So olivine is relatively poor in silica relative to some of the other minerals, and it also takes out magnesium and iron, primarily magnesium in its earliest formation. So you can see that we've got these arrows where the magnesium and iron has been taken out of that melt. So what's going to happen to that melt is it's depleted in those relative to what it started with. So effectively the concentration of the other ions increases. And we're going to spend the next 2 slides looking at this. So the next slide after we've removed olivine would be pyroxene. So if you take out pyroxene, you're looking at calcium, magnesium and iron, plus a little bit more silica than oxygen tetrahedron than we had last time. So you can see that now we've taken out the calcium, magnesium and the iron, that the magma is going to be more enriched in relative terms in the sodium, potassium and aluminium. And this kind of continues, so that as the remaining melt is left after crystallization, so crystallization, you take out these minerals with these particular chemical ions. So your melt, so if you think of it, it's all in relative terms, so relative to what you started, you'll have taken out the magnesium, iron and calcium, and the resultant melt, or the remaining melt, will be higher relatively in silica, sodium, potassium and water. So by a process of this is how you can evolve what we call, is kind of like a chemical evolution of a magma, so that you can form these olivines and things that give you the ultra-mafic or mafic rock types at the base first, so they crystallize out, and then over time your remaining melt becomes more felsic, so in the end you end up crystallizing things that look like a felsic rock. So you start off with a mafic magma, but you can end up with this range in rock types through over time as you cool very slowly. So as was asked in the audience, so it was Norman Bowen in the early 1900s did a lot of did experiments basically. So he took some basaltic magma, crystallized it, and then noted which ones crystallized out and in what order. So that's just what we've just talked about. So you can see on the left it talks about the temperature of that mineral. So naturally, as you would cool from a higher temperature to a lower, you would expect that the higher temperature minerals crystallize first, and that's what we see. So the olivine crystallizes first, and this is so we're looking at the left-hand side, and this is called the discontinuous series. So it just means that one mineral then replaces the other as you go down. So olivine would crystallize first, followed by pyroxene, then amphibole, and then biotite. And then on the right-hand side, we have the plagioclase feldspars. And these, so what happens for this one is you don't replace one with another in the plagioclase. They have the same structure, but the early one will be more calcium-rich. And as the calcium gets depleted, you'll just incorporate more sodium into the structure. So your plagioclase will still be a plagioclase, but it will change from calcium-rich to sodium-rich down temperature and with crystallization. And eventually, when you get to lower temperatures, you'll then get potassium feldspar, so our K feldspar, our orthoclase, sanidine, and microcline, they would crystallize, followed by, including muscovite mica, and then also quartz at the end. So then that's how you can go from ultra-mafic, mafic, intermediate to felsic through crystallization of a single magma body. So that was the layered mafic intrusions. And then if we move on to the Granitic Batholiths, so Yosemite National Park is a good example where you get these now eroded mountains of what were batholiths, big magma storage areas underneath the earth that are now exposed as rocks on the surface. And in terms of a granitoid rock, so we have granite and we have granitoid. Now granitoid just means a term that's loosely applied to a range of felsic plutonic rocks that contain feldspar and quartz. And we'll use a diagram. I can show you the diagram based on their mineral mode, so based on what percentage of minerals they have in there, we can classify them to give them names. So a granite itself is defined as a granitoid, which has roughly equal proportions of quartz, potassium feldspar, and plagioclase. So we've got these huge volumes of felsic rocks, so massive mountains, long chains of batholiths. Now, if we were going to go on the last explanation in that we form evolved rocks through crystallization of a mafic rock, you would need an absolutely massive amount of mafic rock to get anywhere near the amount of felsic rocks we get, because if you think these would just be a small fraction of the end melt, And we just don't see that. So we know that there are some other alternative processes required to actually form these huge amounts of felsic plutonic rocks. So in terms of what granitic batholiths are, there's a few broad generalizations to kind of help us on our way to understand how they can form. So we often find these granitoid rocks in areas where the continental crust has been thickened by mountain building. So areas such as continental arc subduction or collision of sialic, so sialic masses, sialic being silica-rich and aluminium-rich rocks. They also can post-date some of these collisional events as well by millions of years. So that's one factor that we've observed. And because the crust itself is solid in its normal state, it's pretty cool, we know that we need some sort of thermal disturbance or some sort of extra heat or additional heat to form these granitoids, so to melt things. So most people are of the opinion that as well as we can form some of these rocks by fractionally crystallizing, so this progressive crystallization of a mafic melt, a lot of them are derived from partial melting of crustal material, which is called crustal anatexis. So the mantle might provide the source of heat for some of this melting. So if you've got a magma there, it might help with the heat for that, or it could actually be the source itself. So in terms of classifying these granitic type rocks, these granitoids, there's the IUGS classification, which is based, I'll show you this in the next slide, is based on the modal mineralogy, so it's based on the amount of quartz, alkali feldspar and plagioclase that you see. And this gives you this whole range, so this wider range of compositional names for plutonic rocks than we saw for the volcanic rocks. So you can get diorites, tonalites, granodiorites, quartz monzonites, granites. There's the whole range of them. You can also classify them on their alumina saturation. So it's all based on whether there's kind of extra alkalis around or deficient alkali relative to that you need to actually make a feldspar, which has aluminium within its structure. So these can be classified as puraluminous, metaluminous, or puralkaline. So I'm going to show you slides with all these on. And then there's also a classification based more on the kind of tectonic setting that you might find these on and what the protolith. So the protolith just means what it was before it was a granite. So what did you actually melt to form that granitoid rock? So it could be an igneous rock that you melted, it could be a sedimentary rock, or we also have this anorogenic type rocks form. And you get variations in types with tectonic setting, and I'll show you a summary diagram of that. So if we look at this IUGS, so it's the International Union of Geological Sciences classification. So this is a common one, and I think you're going to use this maybe in the prac this week. So you can see that based on, at the top of the apexes of this first triangle, so ignore the bottom half for now, we've got Q, which stands for quartz. On the left lower, we've got A, which stands for alkali feldspar. And on the right-hand side, we have P, which stands for plagioclase. And how it works is if you think of that each of those apexes of that corner, so the Q, the A, and the P, all represent 100% of that component. So if we take quartz, for example, on the top one, so if you were at the very top of where Q is, you would be at 100% quartz. And then if you had 0 quartz, you would be on that line that joins A to P. So that's 0 quartz. So it moves up, so you'd be moving parallel. So horizontal, it would be like a horizontal line that would divide between that baseline to where Q is by, if you think, divide it by 100, and that would be 100%. So if you pick somewhere that was 50% quartz, you would be pretty much, in terms of a horizontal from a top to bottom, you would be in the middle of where that diagram is. Now if we had, same with the A for the alkali feldspar, so if you're in that lower left, if you were right on that A, you would have 100% alkali feldspar. Whereas if you were on the line that joins Q to P, you would have 0% alkali feldspar. So you can see that, for example, if you have a very low percent, so if you had maybe 0 to 10% alkali feldspar and about 50% quartz, you would be in the tonalite field. Can everybody see that? Because I think you're going to have to classify some plutons this week. So you can see also on this that we mentioned before that a granite is roughly equal proportions of quartz, alkali feldspar, and plagioclase. So if you think it has 50% of all of those, then you can plot it on here. So if you had 50% quartz, it would be halfway in terms of a vertical. And then if you had 50% alkali feldspar and 50% plagioclase, you can pinpoint exactly where you would be and name the rock. So because we've got coarse-grained rocks, we can actually quantify what those minerals are, so we can name it like this, whereas for volcanic rocks, you can only really see the phenocrysts. You'd have to then go to the microscope to see actually what the fine-grained part is of the rock. And sometimes in the ground mass, it's impossible, even with a thin section, to determine what the composition is. So you can see it's much easier, and that's why we have a wider range of names to classify them for plutonic rocks. So that's the way. So just make sure you're kind of familiar with how to use that triangle diagram, because it's probably quite a new thing to most people, but you're going to get a bit of practice this week on that. So the second way we can classify them is based on their alumina saturation. So you've got three different types here. You can see that the alumina concentration for each one is the same, but what varies is the alkaline minerals, so the calcium, potassium, and sodium. You can see that on the left hand we have, in relative terms to the alumina, we've got less, and then on the right we've got more, and in the middle we've got a little bit more, but it's quite similar. So based on the ratio of the chemical components of alkalis relative to the alumina, we can classify them as per aluminous if you think they have more alumina, and per alkaline if they have more alkaline minerals. And this is all relative to what you need to put in a feldspar. It's pretty much if you've got extra stuff left or you're deficient, you can't form your feldspars. And these, then you can determine what type of minerals you will form based on these scenarios. So you can get some kind of weird alkaline minerals, so agerine, ribokite, and arfedsonite if you're in the per alkaline group. Kind of more normal situation is meta-aluminous, where you have kind of enough to make what you want, and then you can form extra to that pyroxene, hornblende, and biotite. And then if we have per-aluminous rocks, so we get these alumina-rich minerals, so there you've got the micas, and then some other minerals that we're not worried too much about at this stage. And then the final classification is that by Chappell and White, and where we've got different types of plutonic rocks classified by what they were formed from. So we have S-type granites and I-type granites. So I standing for igneous, S standing for sedimentary. So this just means, again, protolith just means what it formed from. And you'll come across this term when you do metamorphic rocks. So if you had marble, the protolith would be limestone. So it's just what you form from. So so then the next type is these anorogenic granites, which generally form above quite dry areas and from volcanic hotspot activity. And then the next type you have are these mantle type or mantle derived granites. And this covers these that are formed from crystallized mafic magmas, which we said are those small, probably a small fraction of the granites that we actually see on the Earth. So from this fractional crystallization of the minerals. So this was a diagram that's put together that summarizes everything for the classification of granitoid rocks based on its tectonic setting. And you can see we've got orogenic rocks, so those from kind of where you form in mountains or collision or convergence, versus the anorogenic ones, so ones that are formed without this kind of convergence. There's some examples there. And then there's also what the geochemistry is. So you can see here where the M types, the I types, the S types, where they fit in. And also then linked to this alumina classification as well, whether they're metaluminous, per-aluminous, per-alkaline. And it also gives you the rock types and the origin, so what they form from, whether it was the partial melting of mantle-derived or from more sedimentary material. and the melting mechanism. So this is just a summary diagram that I'll let you review in your own time, because there's quite a lot of information there to go through. Okay, so in terms of the evolution of magmas, so after we've partially melted this material, whether it's mantle material that forms a mafic rock, or whether it's higher in the earth and you've melted some of the crystal material, a magma can change its composition, or what we call, it can differentiate, so magmatic differentiation, by three main processes. The one that we've already focused on a little bit when we looked at the layered mafic intrusions, and that's this fractional crystallization. So where you separate from the melt these crystals that you form, or minerals that you form earlier. So that's fractional crystallization. We can also have assimilation. So where you change the magma's composition by incorporating the surrounding rock. So if you think that in some situations where you have hot enough magma, you can start to melt some of that rock that's around you and incorporate that into the melt itself. And you can track these processes with geochemistry. So if you study these rocks, you can model these processes and identify for each volcano. So you can take the volcanic rocks on the surface, or you can take the plutonic rocks, and you can model their changes in composition, and you can identify these things. So isotopes are very good for tracking some of these processes. So assimilation, for example, you might start off with a mantle rock is relatively characterized by a low strontium isotope ratio. This part's just for your information to show how we can track it. But the crustal rocks that have been there for a long time will develop a high strontium isotope ratio. So sometimes what you can see, particularly in some volcanic rocks or in some rocks, is that with evolution, so as your magma's been sat there over time and it's evolving through fractional crystallization, it kind of incorporates more and more of the surrounding rock. So what you'll see, we know that silica content increases as you go from mafic to felsic, so as your rock's evolving, but what we also see is a change in isotope ratio. So if you go from low strontium isotope ratio to high strontium isotope ratio, with the evolution of the magma, then we can identify, okay, you've probably had crustal assimilation. You've incorporated some of that higher strontium isotope ratio crust into your magma as it's been sat there evolving. So imagine if you didn't have any crustal assimilation, your isotope ratio would just be flat. It wouldn't change with evolution. So geochemistry can be a very powerful tool to interpret some of these magmatic processes. And the third type we can have is magma mixing. So if you imagine that systems aren't so simple as that you have a magma sat there, and it erupts and it crystallizes, you might get subsequent pulses of magma coming through and mixing with that magma. So if you have a magma that's sat and crystallized a little bit, evolved a bit, just changed its composition, then you have another impulse of a more mafic, parental, in terms of the more basic magma, then you can get mixing in that system as well. So you can create an intermediate composition, if you like, if you mix a more evolved with a less evolved magma. So this is just a diagram that summarizes those three things. So you can see that on the upper left, we've got assimilation. So this is where you incorporate some of that host rock into the magma, and it might be small enough so that you can sufficiently melt it, or it might be hot enough so that you can sufficiently melt it and incorporate that, melt out that host rock and incorporate it into the magma. Then the lower left, just examples what we've been looking at with the Bowen's reaction series and how we evolve magma composition in these layered mafic intrusions, where the earliest form minerals settle out and form these cumulates, so these layers at the bottom of the magma chamber, or potentially towards the sides. And then this changes the resultant melt composition. So you've taken out those minerals of a particular chemical composition, depleted it of that particular chemical or ion, and then the melt evolves accordingly. And then we've got an example on the lower right where we've got of magma mixing. And it might not be as basically simple as that, where it looks like you've just mixed two magma chambers. It's probably more likely that you have this kind of input through the same system into the same chamber or into the same layer when you mix the magma. So if we summarise the things we've learnt today, we know that plutonic rocks, or intrusive rocks, crystallise before they reach the surface. And because of that, this slower cooling that they have, because the temperature isn't as cold as at the surface, they largely have this larger grain size. So coarse rocks, you know that they're going to have cooled more slowly. The crystals the minerals and crystals are larger in the rock, so they've formed over longer periods of time and at depth in the earth. Now we know that for the ones that are in place at shallow levels, such as these dikes and sills, they might be kind of finer grained. So it's not conclusive, but if you find a coarse grained igneous rock, then you know it's cooled more slowly. And then these are exposed at the surface via erosion and uplift. And we can classify them based on their size, whether they're large or small. So it can be a stock if it's less than 100 kilometers squared for a pluton, or if it's greater than 100 kilometers squared, we'll call it a batholith for these massive ones. The shape of it, so we have tabular and massive. So tabular plutons are dikes and sills, the massive ones being the batholiths and the stocks. We also classify in relationship to the country rock or the host rock. So if you've got a sedimentary rock there with bedding layers, whether it cuts across that layering, so it's discordant, or whether it's parallel to that layering, we call it concordant. And then we looked at two different types of massive plutons, so layered mafic intrusions, where it's just the result of a simple input of magma that crystallized. You formed these denser minerals first that fell and settled at the bottom and formed these cumulate layers, and then the melt progressively became more evolved in composition, more felsic in composition towards the end. Or we have Granitic Batholiths that we can classify based on a whole range of schemes, have a lot more names for them, and they can form also from more complex ways. So you can melt crystal rocks, you can actually evolve them through fractional crystallization. And then we looked at just now at the three main ways that you can evolve a magma. So you can chemically evolve it to become more felsic over time. So this is fractional crystallization, so mineral settling, assimilation of country rock, where you incorporate that material from the surroundings into the magma, and also by magma mixing itself. And then I think there's just a few more slides just talking about the evolution of magmas that you can look at in your own time. Thanks.
Advance to the end of this section for a continuation of the lecture. Recording of the next section of this lecture has been muted for copyright purposes. Please advance to the end of this section for a continuation of the lecture. Recording of the next section of this lecture has been muted for copyright purposes. Please advance to the end of this section for a continuation of the lecture. Recording of the next section of this lecture has been muted for copyright purposes. Please advance to the end of this section for a continuation of the lecture. Recording of the next section of this lecture has been muted for copyright purposes. Please advance to the end of this section for a continuation of the lecture. Recording of the next section of this lecture has been muted for copyright purposes. Please advance to the end of this section for a continuation of the lecture. Recording of the next section of this lecture has been muted for copyright purposes. Please advance to the end of this section for a continuation of the lecture. Recording of the next section of this lecture has been muted for copyright purposes. Please advance to the end of this section for a continuation of the lecture. Recording of the next section of this lecture has been muted for copyright purposes. Please advance to the end of this section for a continuation of the lecture. Recording of the next section of this lecture has been muted for copyright purposes. Please advance to the end of this section for a continuation of the lecture. Recording of the next section of this lecture has been muted for copyright purposes. Please advance to the end of this section for a continuation of the lecture. Recording of the next section of this lecture has been muted for copyright purposes. Please advance to the end of this section for a continuation of the lecture. Recording of the next section of this lecture has been muted for copyright purposes. Please advance to the end of this section for a continuation of the lecture. Recording of the next section of this lecture has been muted for copyright purposes. Please advance to the end of this section for a continuation of the lecture. Recording of the next section of this lecture has been muted for copyright purposes. Please advance to the end of this section for a continuation of the lecture. Recording of the next section of this lecture has been muted for copyright purposes. Please advance to the end of this section for a continuation of the lecture. Recording of the next section of this lecture has been muted for copyright purposes. Please advance to the end of this section for a continuation of the lecture. Recording of the next section of this lecture has been muted for copyright purposes. Please advance to the end of this section for a continuation of the lecture. Recording of the next section of this lecture has been muted for copyright purposes. Please advance to the end of this section for a continuation of the lecture. Recording of the next section of this lecture has been muted for copyright purposes. Please advance to the end of this section for a continuation of the lecture. Recording of the next section of this lecture has been muted for copyright purposes. Please advance to the end of this section for a continuation of the lecture. Recording of the next section of this lecture has been muted for copyright purposes. Please advance to the end of this section for a continuation of the lecture. Recording of the next section of this lecture has been muted for copyright purposes. Please advance to the end of this section for a continuation of the lecture. Recording of the next section of this lecture has been muted for copyright purposes. Please advance to the end of this section for a continuation of the lecture. Recording of the next section of this lecture has been muted for copyright purposes. Please advance to the end of this section for a continuation of the lecture. Recording of the next section of this lecture has been muted for copyright purposes. Please advance to the end of this section for a continuation of the lecture. Recording of the next section of this lecture has been muted for copyright purposes. Please advance to the end of this section for a continuation of the lecture. Recording of the next section of this lecture has been muted for copyright purposes. Please advance to the end of this section for a continuation of the lecture. Recording of the next section of this lecture has been muted for copyright purposes. Please advance to the end of this section for a continuation of the lecture. Recording of the next section of this lecture has been muted for copyright purposes. Please advance to the end of this section for a continuation of the lecture. Recording of the next section of this lecture has been muted for copyright purposes. Please advance to the end of this section for a continuation of the lecture. Recording of the next section of this lecture has been muted for copyright purposes. Please advance to the end of this section for a continuation of the lecture. Recording of the next section of this lecture has been muted for copyright purposes. Please advance to the end of this section for a continuation of the lecture. Recording of the next section of this lecture has been muted for copyright purposes. Please advance to the end of this section for a continuation of the lecture. Recording of the next section